Hi, in this video I'm going to do something very similar to the last video, but instead of applying a unit step function to the RC circuit, I'm going to apply a short pulse of width tau. So Vn of t equals u of t minus u of t minus tau. Here's our time axis, here's Vn of t. It's 0 for t less than 0, then add t equals 0, it jumps up to 1 volt. Then add t equals tau, it goes back to 0 volts. To find the output of the RC circuit for this input, I'm going to use the fact that the RC circuit is an LTI system, and I'm going to find the output of the RC circuit when the input is u of t and u of t minus tau, and then subtract those. So the RC circuit is LTI. Why? Because, as we saw in the previous video, it can be described by a linear constant coefficient differential equation. It's described by a linear constant coefficient differential equation, and any system that is described by a linear constant coefficient differential equation is an LTI system. So it's LTI, which means that I can use the properties of linearity and time invariance to find the output for this input. So for u of t as the input, we saw in the previous video this is the step response, which is 1 minus e to the minus t over ic u of t. Now, if I pass in u of t minus tau to the RC circuit, this is the same thing as u of t, just shifted to the right by tau units. And by the property of time invariance, if I shift the input by some time tau, the output will also get shifted by the same time tau. So therefore, this will go through the LTI system, and I'll get out 1 minus e to the minus t minus tau over ic times u of t minus tau. Now I can combine both of these results and use the property of linearity of LTI systems. So by linearity, the output V out of t is going to be the difference of these two outputs, because the input is u of t minus u of t minus tau. So by linearity, the output is going to be the first output minus the second output. So it equals 1 minus e to the minus t over ic u of t minus 1 minus e to the minus t minus tau over ic times u of t minus tau. And to simplify this a little more, I'm going to write it as a piecewise function. So for t less than 0, it's 0. 0 for t less than 0. For t is between 0 and tau, we're only going to have the first term. So 1 minus e to the minus t over ic. And now, for t is greater than tau, we're going to have 1 minus e to the minus t over ic minus 1, I'm going to distribute the minus, plus e to the minus t over ic times e to the tau over ic for t is greater than tau, and which, as we can see here, the ones will cancel out, and we can factor out e to the minus t over ic, which gives us v out of t equals 0 for t less than 0, 1 minus e to the minus t over ic for 0 less than t less than tau, and e to the minus t over ic times e to the tau over ic minus 1 for t is greater than tau. And this is the pulse response of the RC circuit.